Hello, everybody. Mr. Hennon here. We are going to be talking about tension and the Atwoods machine. So I've got two people here. This is George Atwood, who developed the Atwoods machine, which was really just designed to study Newton's laws of motion. So they really kind of go together. It's nothing new. But one of the things I want to talk about is if you have a rope or a string or a chain or a cable, when you pull on that object, you apply some kind of force on it. So I'll call this a tension force, and you're pulling on it. We know you're pulling on the string, but the idea of it, when it becomes tight, when it becomes taut, whichever term you want to use, basically what it's going to do is it's going to transfer that force to the actual object. So now your FT, your tension force, is applied here. And that's the whole purpose. If you apply a force on one side, then the other side of it is also going to be under a tension. Those tensions have to be the same, and that's what it does. It transfers that. So if I pull down on a rope, for example, it basically transfers that, so it pulls up with a tension force, an Ft on this side. Now, in respect to Newton's third law, we know it would also apply a tension force back on me. So I would actually have a little Ft acting on me. Make things easier, we often talk about massless ropes in physics, so we don't worry about the mass of the rope. We also talk about frictionless, massless pulleys. So we're not going to take those into account. Later on, we'll talk a little bit about how a pulley kind of affects things. So here is actually what we have for an Atwoods machine. An Atwoods machine is just two masses connected by a string over a pulley. That's really all it is. What I'm going to try to look at today are these two things. We're going to try to find an equation for finding the acceleration of them and for finding the tension in them. And then I'll finish it out by showing if I were to put in some masses here, what would happen. In this particular problem, the first thing we have to do is realize that these two masses are going to accelerate in some fashion. So I'm going to borrow their idea. If I know that this is around 4 kilograms and this is around 2 kilograms, I know that this object would be accelerating upward and this object would be accelerating downward. However, since they're attached to a string, as long as that string doesn't break or bunch up, the accelerations have to be the same. But the weird part is we have to pick a direction for the acceleration, but it's all the same acceleration. So here's what I mean by that. Let's say I say on the left side that it's moving upward, and I say I'm going to make that positive. So if something is acting upward on the left side, that's positive. If this thing were to accelerate downward, that would be negative. And I use this for both my acceleration and my forces because that's what they deal with. Now, normally on the other side, I would say, oh, well, down is negative and up is positive. But since this motion, all of this is the same, what that means is coming down on this side is positive. And if you were to go up, that would be negative. This is really weird because what I'm doing is I'm basically connecting these two as direction like clockwise or counterclockwise on the pulley. The next step I'm going to do is we're going to look at the forces acting on this thing. So let's start out by changing our color here. Each one of these is going to have gravity acting downward on it. So I would have a force of gravity acting downward on this one, and I would have a force of gravity acting downward on this one. The force of gravity here I'm going to call Fg1, and this one I'm going to call Fg2. Other forces that I would have on here is they're connected by a string. This is why I started this off. So there would be a tension force that's applying upward on this one. So there'd be an Ft. Since I think this one's going to accelerate upward, this tension force would actually be greater than my weight, my force of gravity. Since that transfers over here, it's not pushing against this, but that's what I was talking about. On the object itself, the object pulls against the string or the rope, and the rope pulls back on it, so it would also feel a tension force. The cool part is these two are the same tension force because they're the tension in the string. So here's what I'm going to do. I'm going to follow Newton's second law for each of these objects. Let's start with this one over here, mass number 1. So the net force on mass number 1, the net force, would equal mass number 1 times the acceleration. Well, how do I find that net force? I have a tension force acting upward, and then I have the force of gravity acting downward. Tension, and this would equal M1 times A. And then if I rearrange this a little bit more, I can write this out that the tension force, and what I'm going to do is I'm going to add this to the other side. So it would equal mass 1 times acceleration plus it would be equal to the force of gravity on 1. But I'm going to do one last thing. So the tension force is equal to mass 1 times acceleration plus mass 1 times acceleration of gravity, because that's how I find that. So what I've done is I've come up with an equation for finding the tension force. That's kind of one of the things we were doing, but it's a little more complicated than that, because right now I don't know the acceleration or the tension force. So I have two unknowns. I can't actually find the tension force without the acceleration. So let's come over here and let's look at the other object. I'm going to switch to a different color. Let's do purple so you can kind of see it. So now I'm going to look at object number 2. So it also has a net force acting on it. It would equal mass 2 times acceleration. Its net force is a little bit different because we want the acceleration to be positive, just to make it a little bit easier. Then I have the force of gravity on object number 2 is in the positive direction, but the tension force is actually in the negative direction. And that would equal mass 2 times acceleration. I'm going to do the same thing, but I'm going to do it a little bit differently. I'm going to add the tension force over to this side, and I'm going to subtract this stuff over to that side. So I'm going to write it as Fg2 minus mass 2 times acceleration would equal my tension force. And then last but not least, do the same thing I did before. So I've got mass 2 times gravity minus mass 2 times acceleration equals my tension force. So I have another equation for the tension force. Now where it kind of comes a little bit strange. So the first part here, it says find the equation for the acceleration of the two blocks. So what I'm going to do is I'm going to jump to a new page, but I'm going to borrow these two equations right here and use them to kind of figure some stuff out. So I'm going to jump to a new page. I'm going to switch to red, and what I have is I know that the tension force is equal to mass 1 times acceleration plus mass 1 times gravity. I also know that the tension force was equal to mass 2 times gravity minus mass 2 times acceleration. These two should equal each other. So if they equal each other, then I can write it like this, that I have mass 1 times acceleration plus mass 1 times gravity equals mass 2 times gravity minus mass 2 times acceleration. So now what I have is I have a kind of a neat way that I'm going to try to solve for A. So what I'm going to do is I'm going to add this to this side, and then I'm going to subtract this to get it over to this side. So I'm putting all the acceleration stuff on one side. So what I end up with is I have mass 1 times A plus mass 2 times A. Over on this side, however, I have mass 2 times gravity minus mass 1 times gravity. Next step I always like to do is I'm going to factor this A out. So it's going to be acceleration. I'm going to write this a little bit different. You'll see in a moment why I'm going to do this, but I'm actually going to flip it around. So I'm going to write it as mass 2 plus mass 1. But we know that you can flip, the summative property of things that A plus B equals B plus A. And then over here, I'm going to factor out the G. So this would end up being G times mass 2 minus mass 1. And then last but not least, let's divide by this stuff. That's going to get rid of it over on that side. I'm just going to use the power of the eraser here. Bye-bye. And what I end up with is this is going to find my acceleration. So if I wanted to find the acceleration of these two things, I actually take gravity, 9.8, times the difference in masses over the sum of the masses, which is kind of neat. So if I was doing this for our particular problem, they said that this one was 4 kilograms and this one was 2. I can find their acceleration. Actually, let's change the color so you realize that I'm doing something different here. That my acceleration would be 9.8 times the ratio of 4 minus 2 over the ratio of 4 plus 2. So 4 minus 2 is 2, and 4 plus 2 is 6. This is going to be 1/3. So the acceleration would be 1/3 of 9.8. Pull out my handy-dandy calculator. 9.8 divided by 3 is 3.26 repeating. So by being connected this way, these masses would accelerate at 3.26 meters per second squared. This one's going to accelerate upward at that rate, and this one's going to accelerate downward at that rate. But I have now found the acceleration. Neato, right? Next step, let's see if we can take these same two equations, and this time we're going to see if we can actually go about finding an equation for the tension force. So I have one equation for finding acceleration. Let's see if I can find the tension force. In other words, how much tension is this in? Usually we don't do this as much, but I want to set this up so we can kind of work this idea. So I'll start with what I had before, that Ft equals m1a plus m1g. And then I have Ft is equal to m2g minus m2a. For this one, I need to solve each one of these for the acceleration. So if I try to solve this one for acceleration, I'd basically be subtracting my m1g and then dividing by m1. So I would have Ft minus this m1g all over m1. That's what a would equal. And then when I do it for this one, I would actually add, nope, let's switch this around. So I would take this m2g, I would subtract it over, and then divide by a negative m. So that's basically going to flip it around. So what I'd have is I'd have m2g minus Ft all over mass 2 would be my acceleration. So which I can kind of see this, if I go back a few slides, you can kind of see that I have that idea from this, that if I take this idea, this Fg2, and it's equal to Ft, if I add that and kind of divide, I would be at the same things that I was doing before. So I'd be adding the m2a, whoops, I would be subtracting and then dividing, yep. Okay, now I can set those two equal to each other. So I've got Ft minus m1g over m1 equals m2g minus Ft over m2. So now I'm trying to solve for Ft. I'm trying to get Ft all by itself. So I probably need to get some kind of setup where I can have the Ft's all by themselves. So it might be easier if I do some kind of cross multiplying. So that's what I'm going to do at this stage. So let's just cross multiply. So I have m2 times this fraction, or this binomial, sorry. And then I have m1 times this binomial. Now at this stage, probably a good place is we can kind of bring all the m1s together. I can divide both sides by m1, and then I just have this all by itself. But the hard part is when I try to bring this Ft over, I'm gonna have to distribute this through first. So if I distribute this through, I'm gonna write this out, that this would be m2 over m1 times Ft. And then when I multiply this, it's going to be minus, the m1s will cancel, but then I'll have m2. So it'll be minus m2g. And over here, I have M2G minus FT. I'm in the way here, so move me over here. Next up, let's bring all the FTs together. So let's add, oops, stopped my thing here. Didn't mean to do that. Let's start up from the current slide. Occasionally it doesn't recognize my pin. It thinks I'm just clicking on it. So I'm going to add this M2G to the other side. And then I'm going to add this FT over. So when I do that, if you notice what I end up with is I've got two of these MG2s, and then I'll have this kind of sum. So I'll have, kind of running out of room here. So I'll have FT plus M2 over M1 times FT, and this would equal 2 of these M2Gs. In other words, twice that mass. And then last but not least, I could factor out this FT. That's going to leave me with 1 plus M2 over M1, and I can divide that over. So here's my ultimate setup. I have FT would equal 2 of these M2Gs over 1 plus M2 over M1, like that. And ta-da, I have a nice little equation of finding FT. Now we don't do this one very often, but we could. And if you notice, basically what we have is mass number 2 is coming in. We have the ratio of the masses. You could multiply top and bottom by M1 so that you get rid of it. And another way I've seen this written, if you multiply top and bottom by M1, is you end up with 2 M1 times M2 times G over M1 plus M2. So you have 2 times the product of the masses times gravity over the sum of the masses. Either one will work. So I could plug in my numbers. So I could take 2 times 4 times my 9.8 and then divide it by the 4 plus 2 or the 6, and then kind of work that out. That's going to give me what on the top? 2 times 4 is 16 times my 9.8 is 156.8, and then divide by 6. And I get 26.13 newtons. So the tension in this rope would be a little over 26 newtons. Now, this is a little bit different because if I think about each object, the 4 times 9.8 is 39.2, and the 2 times 9.8 is 19.6. A lot of people just assume that the tension would be the difference between those or the sum of those two. Well, if I take the difference between them, you get 19.6. So it's not the difference and it's not the sum. It's actually almost like an average of the two. What is that? 39.2 plus 19.6 divided by 2. It's not quite the average, but it's pretty close. So we don't use this equation very much, but it is another one I wanted to throw out and just give us a couple ideas. So we have 2 equations. We have one for the tension force. Our more important one is the one for the acceleration. We're going to use this for our Atwoods Machine lab tomorrow, or on Thursday, sorry. And that's basically it. So hope you enjoyed. I'm going to throw a couple of questions into a Google form to go with this and see what we got.